What is the most powerful thing in the universe? Is it the incandescent, almost unimaginable fury of a supernova, a stellar cataclysm so vast, so energetic, that for a fleeting, glorious, yet terrifying moment in cosmic time, it can outshine an entire galaxy, a swirling city of many billions of individual stars? The universe whispers its secrets in many voices, some barely audible, others roaring across cosmic oceans of space-time. Imagine, if you will, a journey not through terrestrial landscapes, but through the very fabric of existence, where the familiar laws of nature are stretched to their absolute limits, and sometimes, perhaps, even beyond. This is an odyssey into the heart of cosmic power, a meditation on forces that sculpt galaxies, birth stars, and orchestrate the grand, indifferent, and often profoundly beautiful symphony of creation and destruction. Is it, perhaps, the silent, inexorable, and utterly inescapable might of a black hole, a true gravitational behemoth that bends the very fabric of space and time into unimaginable, almost paradoxical knots, a cosmic vortex from which not even light itself, the fastest thing in existence, can ever hope to escape? These are not mere academic questions. They are invitations to contemplate the raw, untamed energies that have shaped everything we see and everything we are. Or could it be something even more ethereal, more focused, more insidiously destructive, like a searing, concentrated beam of high-energy radiation, a cosmic death ray, perhaps, that could, in less than the blink of a human eye, erase an entire planet from existence, sterilizing its surface, boiling its oceans, and extinguishing any nascent, fragile spark of life that might have dared to emerge their power in this vast, dynamic, and often surprisingly violent universe. Clearly manifests itself in a truly bewildering, almost infinite, and often quite awe-inspiring variety of different physical forms. Some of these immense cosmic forces are overtly, terrifyingly, and almost indiscriminately destructive, capable of tearing apart entire stars from within, shredding vast, ancient galaxies through colossal collisions, and perhaps even, in their most extreme theoretical manifestations, reshaping the very architecture, the fundamental geometry of space-time itself. Other, perhaps more subtle, yet equally fundamental forces work far more quietly, much more patiently, almost invisibly on cosmic scales, yet they are no less powerful in their ultimate effect. These are the forces that gently, yet persistently, hold the intricate, delicate structures of the cosmos together against the relentless, disorganizing pull of universal entropy. The forces that bind fundamental particles into atoms, atoms into complex molecules, molecules into stars and planets, stars into vast, majestic galaxies, and galaxies, in turn, into immense, interconnected, web-like cosmic superstructures that span billions of light years. And then, beyond these more familiar manifestations of power, there are perhaps a select, enigmatic few cosmic phenomena, certain forces or events, so utterly strange, so profoundly extreme in their physical manifestation, so far beyond our current, limited terrestrial experience and our present theoretical grasp of fundamental physics, that we still, despite all our remarkable scientific progress and our ever-sharpening observational tools, do not yet fully or even adequately understand precisely how they truly work, what their ultimate, deepest origins might be, or what their far-reaching implications might eventually prove to be for the future evolution of the universe, and perhaps, ultimately, for our own distant, uncertain destiny as a species within it. This is a voyage into the melancholy beauty of cosmic apocalypse, not as an end, but as a constant, transformative process. Let us then embark on an intellectual exploration, a conceptual journey to the very edges of currently known physics, and perhaps just a little way beyond those established frontiers, into the intriguing, often unsettling, realm of the truly, unimaginably powerful, the cosmic forces and the cataclysmic events that relentlessly, and often quite spectacularly, push the very known limits of what physical reality itself can seemingly handle, what it can possibly endure without fundamentally breaking down. We will venture, in our minds and through the lens of science, into diverse physical realms where ambient energy densities, fundamental gravitational fields, and other extreme physical conditions reach almost unimaginable, often theoretically challenging, and sometimes even seemingly paradoxical extremes. These are realms where the familiar, everyday laws of nature, as we currently understand them from our relatively placid terrestrial environment, are often stretched to their absolute breaking point, and sometimes, perhaps, even beyond, into entirely new, currently unknown domains of physical law. And it is precisely in these extreme, crucible-like environments that the universe, in its full, awesome, and often terrifying majesty, most clearly reveals its almost limitless capacity for both breathtaking, intricate creation and for ultimate, all-encompassing, and perhaps even beautifully melancholic, apocalyptic destruction. This is, then, a voyage into the very heart of true cosmic power, a profound and perhaps somewhat humbling quest to try and understand the colossal, often invisible, yet undeniably formative titans that relentlessly, and often quite indifferently, shape our universe, our galaxy, our solar system, and ultimately, even our own fragile, precious existence within it. Prepare to witness a universe forged in power, where every ending heralds a new, often violent, beginning. Our grand exploration into the diverse realms of cosmic power begins not, perhaps, with the immediately colossal or the overwhelmingly vast, but rather with the infinitesimally small, with nature's own, incredibly efficient, and almost unbelievably powerful subatomic particle accelerators. On very rare, entirely unpredictable, and spatially random occasions, a single, solitary, fundamental particle, an entity far, far smaller in physical size than any single atom, can silently, invisibly, and with almost unimaginable kinetic energy, strike the tenuous upper layers of the Earth's protective atmosphere. And it can do so with more raw, concentrated kinetic force than a hard, dense baseball that has been pitched at blistering, record-breaking speed by a highly trained, world-class professional athlete. These extraordinary, almost ethereal messengers from the depths of space are the ultra-high-energy cosmic rays, often referred to by astrophysicists by the acronym UHCRs. And these individual solitary particles rank, without any shadow of a doubt, among the most extraordinarily powerful, most energetically concentrated, and certainly most enigmatic subatomic particles ever to have been observed and meticulously studied by modern science. They do not, it is important to note, arrive at Earth in great visible or easily detectable swarms or in ethereal, faintly glowing clouds, as more common, lower energy astrophysical phenomena like ordinary stardust, diffuse interstellar gas, or the gentle, continuous solar winds that constantly bathe our entire solar system typically do. Instead, these unique, ultra-high energy cosmic rays almost always arrive, one by one, sporadically, almost stealthily, and with no discernible advance warning, like infinitesimally small, silent, invisible, yet incredibly potent, microscopic bullets that have been fired with unimaginable force from the deepest, darkest, and most mysterious reaches of distant, intergalactic space. Each one of these individual UHECRs is, in essence, a lone, intrepid, and incredibly resilient cosmic traveler, having successfully, and against immense odds, traversed truly immense, almost unimaginably vast cosmic distances, distances that often span many millions, or in some cases, even many billions, of light years, to finally, purely by chance, reach us here on our relatively small, insignificant planet Earth. And when they do eventually, randomly arrive. When they finally, catastrophically collide with an unsuspecting, ordinary atom of nitrogen or oxygen residing high up in our planet's tenuous upper atmosphere, they sometimes, in that single, almost instantaneous, and incredibly violent interaction, release a concentrated burst of pure energy that is significantly greater by many orders of magnitude than any human-made machine, any terrestrial particle accelerator, no matter how large or sophisticated, has ever, even for the most fleeting, infinitesimal fraction of a second, been able to artificially produce or effectively control here on Earth. The sheer audacity of such a tiny entity carrying such immense power speaks to the universe's capacity for surprise, a subtle violence woven into the quiet of space. To truly, and perhaps somewhat viscerally, put this astonishing, almost unbelievable, natural cosmic power into some kind of relatable, human-scale perspective, consider for just a moment the most advanced, most powerful, and certainly most expensive single-particle accelerator currently existing and operating anywhere on our planet Earth, the magnificent Large Hadron Collider, or LHC, a truly monumental ring of thousands of powerful superconducting magnets and incredibly sophisticated ultra-sensitive particle detectors, a machine that stretches for a full 27 kilometers in its main circular circumference, and which is buried deep beneath the picturesque Franco-Swiss border countryside near the city of Geneva. This absolutely incredible, awe-inspiring machine, a true triumph of modern, cutting-edge engineering, advanced technology, and sustained international scientific collaboration involving thousands of scientists and engineers from all around the world, is designed to accelerate and then smash together beams of ordinary protons, the positively charged, relatively stable hearts of hydrogen atoms, at speeds approaching an astonishing 99% of the absolute, unbreakable speed of light in a vacuum. In doing so, the LHC routinely produces, in these incredibly energetic head-on proton-proton collisions, staggering particle interaction energies of up to 13, or sometimes, with recent upgrades, even slightly more, trillion electron volts per individual collision event. That is, by any normal human standard or everyday experience, an absolutely enormous, almost unimaginable amount of highly concentrated kinetic energy for a single, fundamental subatomic particle to possess. It is certainly enough focused energy, in fact, to allow experimental particle physicists to directly, and with increasing precision, probe the very deepest, most fundamental building blocks of ordinary matter to effectively recreate, for incredibly fleeting, almost infinitesimal instants of time, the extreme ultra-high energy physical conditions that are thought to have existed in the universe's very first fiery moments just after the Big Bang. And it allows them to actively, and with great hope, search for entirely new, currently undiscovered fundamental particles and perhaps even new, unknown fundamental forces of nature that might lie beyond our current, remarkably successful, yet known to be incomplete, standard model of particle physics. But even these truly prodigious, almost unbelievable, human-generated particle energies, as impressive and as scientifically valuable as they undoubtedly are still utterly, almost laughably, and completely dwarfed in their sheer magnitude by those routinely carried by some of these naturally occurring, and still largely mysterious, ultra-high energy cosmic rays that arrive from the depths of space. Some of these individual, solitary celestial interlopers have now been reliably and repeatedly detected by specialized cosmic ray observatories around the world as possessing total kinetic energies of over 100 quintillion electron volts, a truly mind-boggling, almost astronomical amount of energy to be carried by a single subatomic particle. That's literally many millions of times more concentrated kinetic energy per single individual particle than anything humanity, with all its accumulated scientific knowledge and technological prowess, has ever, even remotely, managed to artificially build, control, or experimentally achieve here on our planet Earth. Imagine, if you can even begin to, all that almost inconceivable, focused power, all that incredible kinetic energy, packed tightly, almost impossibly, into something that is physically far smaller in its actual physical size than even a single solitary proton. It's a concentration of raw, physical energy that is almost too much for the ordinary human mind to readily believe or to fully, intuitively comprehend in all its profound physical implications for the nature of the universe. These cosmic whispers carry the echoes of cataclysms, supernova, or the churning hearts of active galactic nuclei. Events so remote their light might have begun its journey before our solar system even formed. Most ordinary, everyday cosmic rays, the ones that constantly, and for the most part, relatively harmlessly, and largely unnoticed, bombard the Earth's upper atmosphere every single second of every single day, are actually believed to be born or accelerated in relatively common, though still impressively energetic, astrophysical events that occur throughout our galaxy. These include, for example, powerful eruptive solar flares that sporadically burst forth from the magnetically active surface of our own Sun, or they can be generated in the rapidly expanding, turbulent shock waves of ordinary exploding stars. The Type II supernova that frequently occur within the confines of our own Milky Way galaxy as massive stars reach the end of their lives. And these more common, almost garden variety, cosmic rays are by direct comparison to their much rarer, much more energetic ultra-high energy cousins, typically quite relatively low in their individual particle kinetic energy, usually ranging from a few million to perhaps a few billion electron volts. Energies that are easily achievable and often surpassed by our modern terrestrial particle accelerators. But these truly ultra-high energy versions, these UHECRs, these champions of the Cosmic Particle Energy League, are qualitatively, fundamentally, and almost certainly in their origin, very, very different indeed. They don't, for instance, seem to originate from anywhere nearby in our local cosmic neighborhood. Their arrival directions on the sky, though difficult to pinpoint precisely, do not correlate well with any known, obvious, or particularly energetic astrophysical sources located within our own Milky Way galaxy, nor even, it seems, from any of our closest neighboring galactic companions within the local group of galaxies. They're almost unimaginable. Immense individual particle energies strongly, almost unequivocally, imply that they must have been somehow accelerated to these incredible, near-light speed, relativistic velocities somewhere very, very far away from us, perhaps originating from sources located many millions, or even billions, of light-years distant, far, far beyond the gravitational confines of our local galactic group, in some of the most extreme, most violent, most powerful, and most energetic physical environments that the entire observable universe has to offer. Supermassive black holes, accreting matter at furious rates, or the hyperviolent aftermath of gamma-ray bursts, remain prime suspects in this cosmic mystery, their distant rage echoing in these solitary, energetic particles. We've only, to date, and despite many decades of dedicated observational effort by specialized cosmic ray observatories around the world, managed to definitively, unambiguously observe and measure a relative, precious handful, perhaps only a few dozen or so in total, of these truly, exceptionally ultra-high-energy cosmic rays. Those possessing individual particle energies clearly exceeding, say, 50 or 60 quintillion electron volts. And unfortunately, to further compound the already immense observational challenge, their incoming incident paths as they traverse the vast, almost empty expanses of intergalactic and then interstellar space, on their long journey towards Earth, are known to be significantly, and often quite randomly, bent, twisted, deflected, and scattered by the relatively weak, but incredibly pervasive and extensive magnetic fields that are now known to thread throughout all galaxies, and also, albeit even more tenuously, throughout the vast, largely empty spaces that lie between the galaxies themselves. So, accurately, precisely tracing these observed UHECRs back from their arrival direction at Earth to their specific, distant, and often very faint points of origin in the deep cosmos, in order to definitively pinpoint their specific cosmic accelerators, is currently a nearly impossible, and certainly a profoundly, exceptionally challenging, observational and astrophysical task for contemporary astronomers and particle astrophysicists. The universe guards its most powerful secrets well, dressing them in veils of distance and magnetic deflection. Furthermore, it's important to realize that these primary incident UHECR particles don't actually, themselves, ever manage to strike the solid ground of the Earth directly, which is, perhaps, quite fortunate for us and for life on Earth in general, given their immense individual energies. Instead, when these highly energetic primary cosmic rays first encounter the Earth's relatively dense atmosphere, they typically, and almost immediately, violently collide with the atomic nuclei of ordinary atmospheric atoms, usually nitrogen or oxygen atoms, residing high up, many tens of kilometers above the planet's surface. This initial, incredibly energetic collision completely, catastrophically smashes those unfortunate atmospheric atoms apart, thereby creating, in its immediate aftermath, a vast, subsequent, and rapidly developing cascade, a veritable, ever-widening shower of myriad other newly created, secondary, and generally somewhat lower energy elementary particles, particles such as pions, kaons, muons, electrons, positrons, photons, and even some neutrinos. One single, tiny, almost infinitesimal, yet incredibly energetic, primary UHECR particle, upon its initial impact with the upper atmosphere, effectively and almost instantaneously sets off an absolutely enormous, spatially extensive atmospheric particle shower. An event technically known to physicists as an extensive air shower that can, by the time it eventually reaches the Earth's surface, have spread out laterally over many square kilometers in area. Specialized, ground-based cosmic ray detectors, often consisting of many individual, widely separated detector stations, are then used to simultaneously pick up, record, and precisely time the arrival of these numerous, spatially distributed secondary air shower particles. Scientists then meticulously try to piece together, through careful, complex computer-based reconstruction algorithms that analyze the precise arrival times, the measured energies, and the spatial distribution of all these detected secondary particles. Precisely what kind of energetic interaction must have happened high up in the atmosphere many microseconds earlier. And from that reconstructed information, They then try to infer, with as much accuracy as possible, what the crucial physical properties, particularly the initial energy, the approximate arrival direction, and perhaps even the particle type of the original unseen primary cosmic ray particle must have been before it initiated that vast atmospheric cascade. This indirect detection is a testament to human ingenuity, turning the atmosphere itself into a vast detector. In very remote, often quite desolate, and geographically extensive places around the world, such as, for example, the vast open pampas grasslands of western Argentina, which is home to the currently largest such facility in the world, the Pierre-Auger Observatory. Dedicated teams of international scientists and engineers have painstakingly built and now operate truly huge, sprawling arrays of these specialized cosmic ray particle detectors. These arrays often consist of many hundreds or even thousands of individual, independent detector stations, which are typically spread out systematically, often in a regular grid pattern over incredibly wide geographical areas, sometimes covering many thousands of square kilometers of terrain, all patiently, continuously watching the skies above, day and night, for the fleeting, telltale observational signs of these incredibly rare, yet scientifically invaluable ultra-high energy atmospheric cascade events. When a primary UHECR successfully hits the Earth's upper atmosphere, it then sends this characteristic, relativistically moving, almost pancake-shaped wave or front of myriad secondary particles cascading downwards towards the ground at very nearly the absolute speed of light. These extensive, ground-based detector arrays then effectively, and with remarkable precision, listen for the precise moment of arrival of that subtle yet detectable particle wave at each of their individual detector stations. And then, by meticulously measuring the precise arrival times and the deposited energies of all the detected secondary particles at these many different, widely separated detector locations across the array, they can then accurately and often with surprising detail reconstruct the overall physical size, the precise three-dimensional shape, and the total energy content of that entire extensive air shower as it swept over the observatory. It's a remarkably indirect, yet surprisingly effective and scientifically robust method of detecting and characterizing these otherwise invisible primary cosmic ray particles. It is, in some ways, conceptually somewhat like trying to accurately figure out precisely what kind of massive, unseen rock made a very big splash in a dark, distant, and otherwise completely inaccessible pond by only being able to carefully look at and meticulously analyze the detailed physical properties of the expanding, concentric system of outgoing water ripples that eventually, and often much later, manage to reach the distant shore where your detectors are located. From the precise shape, the measured amplitude, the arrival timing, and the evolving energy distribution of those observed secondary water ripples, these dedicated scientists patiently, painstakingly, and with great ingenuity, try to accurately learn as much as possible about the original size, the precise incident direction, and most importantly, the incredible, almost unimaginable initial kinetic energy of that original, unseen and long since disappeared stone. The silence of these remote observatories belies the violent messages they strain to hear from the cosmos. Even though we, as a global scientific community, have now successfully built these truly enormous, incredibly sophisticated, and often quite expensive, dedicated ground-based observatories specifically to try and systematically study them, these truly ultra-high-energy cosmic rays, the most energetic particles known in the universe, still remain exceptionally, almost frustratingly, rare celestial events from our observational perspective here on Earth. On average, Current best estimates from these observatories suggest that only about one single such UHECR, possessing an individual particle energy clearly exceeding, say, 50 or 60 quintillion electron volts, actually physically hits each single square kilometer of the Earth's entire upper atmosphere roughly only about once every century or so. That incredibly low arrival rate means, quite starkly, that you could patiently, diligently, and with unwavering dedication watch the entire sky above you, day and night, for your entire human lifetime. And you would still, in all statistical likelihood, never, ever directly, personally witness the arrival or the atmospheric signature of one of these truly extraordinary, universe-traversing, and still largely enigmatic elementary particles. If we could, however, somehow, someday, fully and comprehensively understand their precise astrophysical origins, their currently unknown acceleration mechanisms, and their detailed propagation characteristics as they journey through the vast, magnetized expanses of intergalactic and interstellar space, then we might, just might, be able to gain invaluable, perhaps even revolutionary, new physical insights into some of the most extreme, most energetic, most violent, and currently most mysterious physical environments that are known to exist anywhere in the entire observable universe. We might even, perhaps, if we are particularly fortunate and insightful, stumble upon entirely new, currently unknown, and perhaps even paradigm-shifting laws of fundamental physics, new physical principles, new particles, or new interactions that only truly manifest themselves, or become clearly apparent, at these almost unimaginably high, ultra-relativistic energy scales that are currently far, far beyond anything we can even remotely hope to achieve or to directly probe. In our most powerful cutting-edge terrestrial laboratory experiments and particle accelerators, perhaps these lone voyagers carry clues to the very texture of space-time or the echoes of creation itself. The universe, it seems, still holds the championship title for high-energy particle physics, a humbling reminder of our nascent understanding. Now, let us turn our scientific attention, and our perhaps somewhat apprehensive human imagination, from these tiny, individual, almost invisible, yet incredibly, almost unbelievably energetic cosmic ray bullets, particles which, as we've noted, typically travel largely alone and almost entirely unseen through the vastness of the cosmos until they happen to strike our atmosphere. Let us shift our focus instead to something far more tangible from our everyday experience, far more immediately visceral in its potential impact, and certainly, potentially far more directly, globally, and apocalyptically destructive on a planetary, and perhaps even a biospheric scale, namely, the cataclysmic, truly earth-shattering, and often species-ending hammer-blow dynamics of what are known as mega-asteroid impacts. Unlike those subtle, individual, and largely indirect cosmic rays, a typical mega-asteroid, one capable of causing global devastation, is a veritable, solid, tangible mountain, often many kilometers across in physical size, composed primarily of dense, primordial solar system metal and heavy stone, hurtling silently, menacingly, and often with very little advance warning, through the cold, dark, and largely empty blackness of interplanetary space. On a potential collision course with a planet like our own Earth, the sheer, almost unimaginable amount of raw kinetic energy that would be instantly, catastrophically released upon its violent impact with a relatively fragile, life-bearing planet like Earth is truly, almost incomprehensibly enormous, far, far beyond, by many orders of magnitude, anything that human beings, with all our accumulated technological prowess and our unfortunate history of destructive invention, have ever, even in our most extreme, globally threatening moments, managed to artificially create or deliberately unleash upon ourselves or our planet. This is not a whisper, but a deafening roar, a cosmic hammer blow that can rewrite planetary history in an instant. A relatively modest, by some cosmic impact standards at least, 10-kilometer diameter asteroid, an object roughly the size of Mount Everest, but composed of much denser rock and metal, and traveling at typical interplanetary encounter speeds of perhaps 20 to 30 kilometers per second, if it were to directly catastrophically strike the Earth, would instantaneously, in a fraction of a second, release more raw, concentrated, destructive energy than all the thousands of powerful nuclear weapons currently existing in the combined arsenals of all the nuclear-armed nations on the entire planet, if they were all somehow gathered together and detonated simultaneously at a single point on the Earth's surface. And that's not just a one-time energy release equivalent, mind you. Such an impact would likely release that much energy, or even significantly more, not just once, but potentially many, many times over, depending on the asteroid's precise initial mass, its exact chemical composition, its incoming trajectory, and its final impact velocity relative to the Earth. The underlying fundamental physics of such a catastrophic cosmic impact event, in principle at least, relatively simple, straightforward, and well understood by planetary scientists and physicists, based on fundamental principles of mechanics, thermodynamics, and shockwave propagation. Yet its predicted and historically observed physical consequences for a planet like Earth, and for any life that might exist upon it, are utterly, almost indescribably terrifying and potentially, truly apocalyptic in their scope and severity. A truly massive, solid object. The asteroid, moving at an incredibly high interplanetary speed, often many tens of times faster than a speeding rifle bullet, carries with it an absolutely immense, almost unimaginable amount of stored kinetic energy. And all that colossal, planet-shattering kinetic energy must, by the fundamental, inexorable, and unbreakable physical law of conservation of energy, go somewhere, be rapidly, violently transformed into other, equally destructive forms of energy, primarily heat, light, sound, and mechanical shock, when that massive, speeding rock suddenly, catastrophically, and almost instantaneously stops its immense forward orbital motion upon impact. It stops very, very suddenly, indeed, in a tiny fraction of a second, effectively smashing violently, almost explosively, into the Earth's relatively thin, fragile solid outer crust, much like a colossal, cosmic-sized sledgehammer, swung with unimaginable force. In the immediate, fiery, and chaotic aftermath of such a truly titanic mega-impact event, the Earth's solid crust, and even parts of its upper mantle, at the precise point of impact, would instantaneously, almost unbelievably, melt, completely liquefy, and even partially vaporize into an incandescent, superheated plasma, all due to the immense pressures and temperatures generated by the sudden, extreme compression of material. This molten and vaporized rock would then be violently, explosively ejected outwards in all directions from the impact site, some of it thrown high up into the atmosphere, some even potentially escaping Earth's gravity altogether and being blasted out into interplanetary space. The ground itself, for hundreds, perhaps even thousands, of kilometers around the impact site, would tremble uncontrollably, violently, almost like the skin of a struck colossal cosmic gong. Immense, powerful seismic shock waves, far, far more energetic and destructive than those generated by even the largest, most powerful naturally occurring earthquakes ever recorded in human history, would rapidly, relentlessly tear their way through the planet's deep rock layers, propagating outwards from the impact point like ripples on a pond, but with far more devastating consequences. These seismic waves would catastrophically crack, shatter, and liquefy the solid surface of the Earth for hundreds, perhaps even many thousands of kilometers in all directions from the primary impact point. Within mere seconds, or at most, just a few short minutes of the initial impact, a truly massive, almost unimaginably large impact crater, a vast, gaping, circular wound gouged deeply into the planet's surface, would be violently, explosively excavated by the sheer force of the impact and the subsequent rebound of compressed rock. Such a crater would often be significantly deeper, by many kilometers, than any human-made excavation ever attempted, and it could potentially measure many hundreds of kilometers in its overall diameter, a truly planetary-scale scar. The melancholy beauty of such destruction lies in its raw, indifferent power, a force that resets planetary clocks. The intense, almost unimaginable heat that would be generated by the initial impact itself, primarily from the extreme, sudden compression of both the impactor and the target rock, and also from the friction of re-entering ejecta, would be more than enough, almost instantaneously, to ignite widespread, raging, and almost uncontrollable fires for many thousands of kilometers in every conceivable direction outwards from the primary impact site. Entire vast continental forests, sprawling grasslands that might stretch from horizon to horizon, perhaps even entire. Unfortunate ecosystems located anywhere within this vast, global inferno would spontaneously, almost explosively, burst into flame, completely incinerating everything remotely combustible that lay within their path. Any animals, any unfortunate, exposed life forms that were unlucky enough to be caught out in the open, anywhere within this vast, rapidly expanding radius of fiery incandescent destruction, simply tragically wouldn't stand a chance of survival. They would be almost instantly vaporized by the intense heat, or quickly burned alive by the ensuing global firestorm. Winds far, far exceeding any normal meteorologically generated hurricane speeds that we are familiar with on Earth today, winds perhaps reaching many hundreds or even thousands of kilometers per hour, would be instantly generated, driven not by conventional atmospheric pressure gradients or differential solar heating of the Earth's surface, but rather by the sheer, raw, explosive, outward propagating force of the impact blast itself. These super hurricane force winds would relentlessly, mercilessly scour the entire landscape, bare for vast distances around the impact site, uprooting trees, leveling buildings, and carrying vast quantities of dust, debris, and burning embers far across continents and even oceans. And, at the same time, almost unimaginable, truly colossal quantities of fine dust, black soot from the widespread global wildfires, shattered rock debris from the impact crater excavation, and various other vaporized terrestrial and impactor materials would be violently, explosively thrown high up into the Earth's upper atmosphere, with some of the finest, highest velocity ejecta particles even potentially reaching up into the stratosphere, or perhaps in the most energetic impacts, even being blasted completely out into space, only to then slowly, gradually, and ominously fall back down again towards the Earth's surface under the influence of gravity, often many days, weeks, or even months after the initial primary impact event had already long since passed. The sky itself would become an enemy, raining down fire and darkness. And as this vast, globally encompassing cloud of superheated atmospheric debris, this choking, sunlight-blocking global shroud of fine impact ejecta, then begins to slowly, gradually, and inexorably fall back down towards the Earth's surface from the upper atmosphere, under the relentless pull of planetary gravity, often many long days or even several weeks after the initial primary impact event itself has already long since concluded. It would then effectively and quite catastrophically superheat the entire planet's atmosphere, primarily through the immense frictional drag it would experience as it re-enters the denser, lower atmospheric layers at very high speeds. This re-entry heating would, according to some detailed scientific models, effectively and quite terrifyingly turn the entire sky all across the whole globe into a glowing, broiling, inescapable, and planet-wide convection oven, literally baking the underlying surface of the Earth below with intense, downward radiating infrared heat for many hours, or perhaps even for several days, potentially killing off any remaining surface life that had somehow managed to survive the initial blast. The fires and the winds, then, inevitably, if the impactor was large enough, would come the colossal, almost unimaginable, globe-spanning, and continent-drowning tsunamis. If the impacting asteroid, as is statistically quite likely, given that well over 2/3 of the Earth's entire surface is currently covered by deep water, were to catastrophically strike one of the planet's vast, interconnected oceans, the almost unimaginable, explosive energy of that underwater impact would then violently displace and powerfully push truly massive, almost unbelievable, towering walls of ocean water outwards at incredible speed in all directions, away from the sub-oceanic impact point. These uniquely impact-generated, colossal ocean waves are predicted to be utterly, qualitatively unlike any ordinary, familiar, and relatively much smaller tsunamis that are typically, and much more frequently, caused on Earth by more conventional geological phenomena. They would be much, much taller in their wave height, potentially reaching many hundreds of meters, or in some extreme impact scenarios, perhaps even several kilometers, in their initial amplitude as they propagate across the deep ocean basins. They would also be much, much faster in their propagation speed, perhaps traveling across entire, vast ocean basins at speeds easily comparable to that of a modern jet airliner, many hundreds of kilometers per hour. And consequently, they would be vastly, unimaginably more destructive, more erosive, and more inundating when they finally, and with little or no warning, eventually reach distant, unsuspecting continental coastlines. Coastal regions, even those that might be located on the very far opposite side of the entire planet from the original remote oceanic impact site, could still be utterly, catastrophically, and completely slammed, many long hours, or perhaps even a full day or more, later by these monstrous towering walls of onrushing ocean water with surging, turbulent waves far, far higher than any currently existing coastal buildings or natural geographical features. Waves that could potentially sweep inland for many, many kilometers, or even hundreds of kilometers in low-lying areas, completely destroying everything, both natural and man-made, that lay within their devastating, irresistible path. The very oceans, cradles of life, would become agents of immense, sweeping devastation. And even after the initial horrific blast wave from the impact has finally, mercifully dissipated its primary energy, even after the searing, incandescent heat has begun to radiate away into space, even after the widespread, raging global fires have at last, perhaps after many weeks or months, finally burned themselves out, and even after the colossal, globe-spanning tsunamis have eventually, after causing unimaginable coastal devastation, finally gradually receded back into their now churned and debris-filled ocean basins, the truly long-term, insidious, and potentially even more devastating global environmental consequences of such a mega-impact event would, unfortunately, only just then be seriously, and inexorably, beginning to fully unfold and make their presence felt across the entire planet. The truly vast, almost unimaginable quantities of incredibly fine dust particles, the pervasive black soot generated from the extensive global wildfires, the shattered, pulverized rock debris that was violently excavated from the immense impact crater itself, and various other complex chemical aerosols and vaporized terrestrial and impactor materials that were explosively, energetically thrown up high into the Earth's upper atmosphere by the sheer, raw violence of the initial impact event, would then likely remain suspended there in the stable, largely weather-free layers of the stratosphere for a very considerable and potentially quite devastatingly long period of time. This global atmospheric shroud would effectively and quite efficiently block a very significant fraction, perhaps even most, of the incoming, life-sustaining sunlight from ever successfully reaching the planet's underlying surface, potentially for many long, dark, and frigid months, or even, in the case of a particularly large impactor or a very fine-grained ejecta blanket, for several long, difficult, and ecologically catastrophic years. With drastically reduced sunlight levels reaching the surface, photosynthesis, the fundamental biological process that lies at the very base of most, if not all, of Earth's complex ecosystems, the process by which plants and algae convert sunlight into chemical energy, would largely, if not entirely, cease on a global scale. Plants all across the world, starved of essential sunlight for their growth and survival, would inevitably and relatively quickly begin to wither, to die, and to decay on a truly massive, planet-wide scale. As a direct and unavoidable consequence of this collapse of primary productivity at the base of the food web, global average surface temperatures would then be expected to plummet dramatically, perhaps by many degrees Celsius, or even by tens of degrees Celsius in some climate models, depending on the amount and duration of sunlight blockage. A kind of artificial, impact-induced, and globally pervasive winter, an impact winter, would then swiftly, inexorably, and quite chillingly settle in across the entire darkened globe. This would be a prolonged period of intense cold and deep darkness. A winter caused not by familiar seasonal variations, but by the profound absence of sunlight at the planet's surface, a chilling twilight for any surviving life. This predicted catastrophic impact winter would in turn inevitably lead to the widespread and likely quite rapid starvation, decline, and ultimate collapse of entire ecosystems all across the world, both on land and in the surface layers of the oceans. Without sufficient sunlight, plants, the primary producers, cannot survive. Without plants, herbivores die. Without herbivores, carnivores perish. Whole, complex food webs that had evolved over millions of years would unravel in a brutal, ecologically devastating period of planet-wide upheaval. The very fabric of life on Earth would be torn asunder. There is at least one chilling, well-documented moment in Earth's history when precisely such a devastating scenario occurred. Approximately 66 million years ago, the Cretaceous-Paleogene boundary event, a colossal 10-kilometer asteroid slammed into what is now the Yucatan Peninsula, creating the Chicxulub crater, over 180 kilometers in diameter. This dinosaur killer is credited with wiping out roughly 75% of all then-existing species. It was not just the impact itself, but the subsequent global wildfires, atmospheric superheating, colossal tsunamis, and, most devastatingly, the prolonged impact winter that followed. Within just a few years, perhaps months, life on Earth was unrecognizably altered. Only the particularly adaptable, often small, organisms managed to survive that global apocalypse. The reign of the dinosaurs ended abruptly, a stark reminder of cosmic indifference. The darkened skies eventually cleared, perhaps after years, and the Earth gradually warmed, but the ecological damage was irreversible. The Chicxulub impact, though uniquely transformative, was not the only such event. Earth's history is pockmarked with scars from other cosmic collisions, some causing regional devastation, others smaller but still locally terrifying. These ancient impacts, evidenced by craters and geological anomalies, remind us that these are ongoing, if rare, processes. Scientists today can simulate these impacts with increasing accuracy, and the predictions are grim. Even a 5-kilometer asteroid could cause civilization-collapsing devastation, obliterating cities, causing global agricultural failure, and leading to widespread societal chaos. Our modern, interconnected world is profoundly vulnerable. The challenge lies in detection. Small asteroids can approach with little warning, while dedicated sky survey programs track larger objects, many smaller, yet still dangerous. Ones pass by undetected until it's too late, or even after they've already passed. Space is vast, and these dark, inert bodies are faint, difficult to spot against the blackness until they are perilously close. International efforts are underway to develop planetary defense strategies, from kinetic impactors like NASA's DART mission to more speculative ideas like solar sails or, as a last resort, nuclear explosives. But these are largely theoretical or in early experimental stages. We have never had to use them in a real emergency. A 10-kilometer asteroid doesn't need to explode. It just needs to land. Its kinetic energy alone is apocalyptic. Despite the danger, there's a grim majesty to these cosmic hammers. They are integral to planetary formation and evolution, delivering water and organic molecules, mixing planetary crusts, and creating new habitats. They are ancient messengers from the solar system's birth, indifferent to our existence, following only the laws of gravity. A constant, if low probability, threat whose melancholy beauty lies in its sheer, transformative, and indifferent power, a power that shaped our world and could, one day, reshape it again. Now, let us broaden our cosmic perspective even further, venturing far beyond the relatively familiar, if sometimes hazardous, confines of our own solar system, out into the vast, dark, largely unexplored, and almost unimaginably empty interstellar realms that lie between the distant, lonely stars. In these quiet, almost unimaginably empty, and incredibly cold reaches of space that exist between the myriad stars of our Milky Way galaxy, there are astronomers now increasingly, and with growing observational confidence, believe countless individual planets that have no home sun, no gravitationally anchoring parent star to faithfully call their own. These are the enigmatic, almost ghostly, rogue planets, the true interstellar orphans of the cosmos, celestial bodies, often of significant planetary size and mass, that were likely, in most cases, unceremoniously, and often quite violently, ejected from their original home planetary systems, perhaps during the chaotic, gravitationally turbulent early stages of their formation around their young, still-forming parent stars. Or alternatively, perhaps they were set adrift, cast out into the interstellar wilderness much later in their system's history, as a direct result of close, destabilizing gravitational encounters with other, more massive planets within their system, or perhaps even with other passing stars or giant molecular clouds that happen to wander too close to their original stellar neighborhood. They now, as a result of these ancient dynamical upheavals, drift, alone, silently, perpetually, and for the most part, almost entirely invisibly to our current telescopes, through the immense, cold, profound darkness of interstellar space, entirely without the life-giving warmth, the illuminating light, or the guiding, stabilizing gravitational embrace of a central parent star to faithfully and predictably orbit. These are often giant, truly wandering worlds, perhaps many of them gas giants as large as, or even significantly larger than, our own Jupiter, or perhaps, and even more intriguingly, from an astrobiological perspective, there are also countless smaller, potentially Earth-sized or Mars-sized rocky bodies among them as well, all forever set loose, untethered from their original home planetary systems, now embarked on an eternal, solitary, and almost unimaginably long journey through the vast, dark, and largely empty expanses of our Milky Way galaxy. Their existence speaks of a dynamic, often violent, youth for planetary systems, a universe less ordered than it might appear. And as these numerous, dark, cold, and incredibly lonely rogue planets move silently, almost ghost-like, and largely undetected, through the immense, almost incomprehensible vastness of our surrounding galaxy, they will, inevitably from time to time, purely by statistical chance and due to their random motions, pass relatively near to other, established, and gravitationally stable stellar systems, systems that may well, and indeed often do, contain their own well-ordered families of already existing, gravitationally bound orbiting planets. The statistical chances of a direct, physical, head-on collision between one of these wandering rogue planets and an established planet within such a system are, admittedly, from a purely probabilistic perspective, incredibly, vanishingly small, given the almost unimaginably, truly mind-bogglingly empty nature of interstellar, and even most interplanetary space. But, and this is the crucial and somewhat unsettling point, these chances are not, from a fundamental physical perspective, absolutely, mathematically zero. And if by some incredibly unfortunate, statistically highly improbable, yet physically entirely possible cosmic coincidence, one of these massive, dark, and silently wandering rogue worlds were to actually physically collide, head-on, or even with a significant glancing blow, with another unsuspecting host planet within an established system, especially if that collision were to occur with a planet roughly the size of our own Earth, or perhaps even significantly larger. Like a super-Earth or a mini-Neptune, then the resulting cataclysmic physical consequences, the sheer amount of energy released, would be utterly, almost unimaginably, beyond anything that we have ever directly witnessed, or could even readily, intuitively conceive of from our relatively limited and thankfully much more placid terrestrial experience of physical impacts and explosions. A direct, head-on, planet-on-planet collision between two full-sized, massive celestial bodies is not, it must be emphatically stressed, in any way remotely comparable to a relatively small, albeit still potentially devastating, asteroid or comet simply hitting the much larger solid surface of another, much more massive rocky planet. These are entire, fully fledged worlds coming together with unimaginable force, potentially possessing molten cores, thick atmospheres, and perhaps even life. Such a collision is a planetary-scale demolition derby, capable of reshaping or even destroying entire star systems. A true cosmic apocalypse where new worlds are forged in fire from the annihilation of old ones. Imagine a large, dark rogue planet, perhaps Earth-sized or larger, drifting alone through interstellar space for billions of years, its surface frozen under a starless sky, its internal heat slowly fading. By chance, it enters a new stellar system over millennia. Its orbit, influenced by the system's gravity, intersects with an established planet. As they inexorably approach, their mutual gravity accelerates them to a final, spectacular, and mutually annihilating rendezvous. At the moment of impact, the energy released is trillions of times greater than any thermonuclear bomb. The surfaces of both planets melt and vaporize. Mountain ranges are obliterated, oceans flash boil into superheated steam. Atmospheres are stripped away and blasted into space. The dense cores of the planets might collide and fuse, forming a new, larger, molten core. The surrounding space fills with a rapidly expanding cloud of glowing debris, shining brighter than nearby stars, a temporary beacon of apocalyptic destruction visible across interstellar distances. If such a collision were to involve an inhabited world like Earth, there would be no warning, no escape. Everything, civilization, ecosystems, life itself, would be utterly erased, buried beneath kilometers of molten rock. Life would not just end, it would be obliterated, its every trace lost in the incandescent chaos. Yet, even in this ultimate destruction, there is a strange, creative potential. The shattered remains of the two planets might, over millions of years, recoalesce to form a single, new, and initially molten world, perhaps larger and more chemically diverse than its progenitors. This newborn world, forged in violence, might eventually cool, develop new geological features, and perhaps, after eons of cosmic convalescence, even become ready for life to arise anew. The universe demonstrates a terrifyingly violent capacity for both destruction and creative renewal. Such world-shattering collisions, though rare in mature systems today, have likely occurred in our own solar system's past. The origin of Earth's moon is widely believed to be the result of a giant impact when a Mars-sized protoplanet named Theia collided with the young Earth. This cataclysm tore off a significant portion of Earth's mantle, which then coalesced to form the moon, forever changing Earth's rotation, axial tilt, and possibly its early evolution. Uranus's extreme axial tilt and Mercury's unusually large core relative to its size may also be scars from ancient giant impacts. These events are not just theoretical. They are part of how planetary systems form and evolve. Scientists estimate there could be as many free-floating rogue planets in our galaxy as there are stars, hundreds of billions, perhaps trillions, drifting silently. They don't even need to collide to cause havoc. A close gravitational pass can destabilize planetary orbits, trigger cometary bombardments, or strip moons from their planets. But a direct hit is a planetary reset button, an event of profound, transformative power. The melancholy beauty here is in the scale of creation and destruction, a cosmic ballet where worlds are unmade and remade. Now, let us turn our gaze from the cataclysmic collisions of entire worlds to the equally, if not more, violent and energetic deaths of individual stars, specifically to a rather peculiar, somewhat rarer, and until relatively recently, not very well understood, type of stellar explosion known as an electron capture supernova. Most people associate supernovae with the core collapse of very massive stars, those more than 10 or 20 times the Sun's mass, ending in a spectacular iron core collapse explosion. But there's another, distinctly different kind of stellar supernova, generally quieter, less luminous, and rarer, originating from stars poised precariously in an intermediate mass range, not small enough to fade peacefully as white dwarfs like our Sun, but not massive enough for the typical iron core collapse. These stars, typically between 8 and 10 or 11 solar masses, die via electron capture. As they near the end of their lives, their cores, rich in oxygen, neon, and magnesium rather than iron, reach a critical density and temperature. Under immense pressure, free electrons are forcibly squeezed into atomic nuclei, combining with protons to form neutrons and releasing neutrinos. This process is known as electron capture or inverse beta decay. Electrons, being fermions, normally provide crucial support against gravity through electron degeneracy pressure, a quantum mechanical effect preventing them from occupying the same quantum state. When enough electrons vanish through capture, this vital pressure support catastrophically drops. With the loss of electron degeneracy pressure, gravity overwhelmingly takes over. The stellar core implodes with shocking rapidity, a near freefall. As material compresses, temperatures and densities soar. Neutrons, newly formed, pack tightly, forming an incredibly dense proto-neutron star at the center. The star's outer layers, rushing inwards, violently slam into this unyielding neutron core. The resulting shockwave rebounds, blasting the star's remaining envelope into interstellar space. This is an electron capture supernova. While not as intrinsically bright as iron core collapse supernovae, these events are crucial. They provide unique clues about stellar evolution, neutron star formation, and the chemical enrichment of the early universe, particularly concerning the production of certain neutron-rich isotopes. They represent a critical evolutionary pathway between the peaceful deaths of low-mass stars and the violent explosions of high-mass stars. Their light curves are often slower, their spectra showing distinct chemical signatures of elements like oxygen, neon, and magnesium, not typically seen in other supernovae. These events may be responsible for a specific subpopulation of neutron stars with characteristic masses, spins, or magnetic fields, and could explain anomalous chemical abundances in ancient, metal-poor stars. They might even trigger new star formation by sending compressive shock waves through nearby gas clouds. The conditions for an electron capture supernova are very specific. The progenitor star must be in a narrow mass range, and its core must develop the right mix of elements at critical densities and temperatures. If the star is too massive, it undergoes iron core collapse. If too small, it becomes a white dwarf. Only a precise evolutionary path leads to this quieter, yet profoundly transformative, stellar end. The neutron stars left behind might also be unique, perhaps quieter and less active than those from more violent explosions, slowly cooling as silent reminders of a less spectacular but equally significant stellar departure. Their quiet beauty lies in their subtle precision, a delicate balance tipped into oblivion. Now, let us turn our attention to an even more extreme, even more violent, and certainly far rarer form of stellar death. A cataclysm reserved only for the true celestial titans, the most massive stars that the universe can possibly create, the pair-instability supernova. Some stars, it turns out, are born so incredibly, almost unbelievably massive, so astonishingly bright and luminous, and so unimaginably hot in their cores, that the usual well-understood rules and physical processes that govern ordinary stellar evolution and eventual stellar death simply don't apply to them in the same way. These truly colossal stars, behemoths perhaps dozens or even hundreds of times more massive than our own relatively modest sun, relentlessly push the very absolute limits of what fundamental physics itself can seemingly handle, what it can stably sustain. Their entire stellar lives, though incredibly brilliant and impactful on their surroundings, are as a direct consequence of their enormous mass and correspondingly prodigious energy output. Tragically, almost poetically, short, often lasting only a very few brief million years at most, a mere fleeting instant on the vast cosmic timescale. But their spectacular, almost incomprehensible ends, when they finally arrive, are correspondingly some of the most extraordinarily violent, most energetically powerful, and most cosmically significant explosive events that can occur anywhere in the entire universe. And for a very select, very specific few of these ultra-massive stars, those falling within a particular critical mass range. Death doesn't come in the usual way, not from the gradual, inexorable collapse of an inert iron core, nor even, as we've just discussed, from a runaway electron capture process in an oxygen-neon magnesium core. It doesn't even primarily come from simply running out of available nuclear fuel to burn in their cores. Instead, these unfortunate, uniquely massive stars literally, and quite spectacularly, explode, not primarily because their cores become gravitationally weak and unable to support their own weight, but rather, paradoxically, because their cores become too energetically strong, too incredibly hot and radiation-dominated. They effectively, and quite literally, destroy themselves completely, from the very inside out, in a truly unique and utterly devastating type of stellar cataclysm known to astrophysicists as a pair-instability supernova. The universe, in these moments, reveals its capacity for absolute, beautiful annihilation. To even begin to understand how this extraordinary and thankfully very rare type of stellar explosion can actually happen, we have to conceptually look deep into the unimaginably extreme physical conditions that prevail at the very heart, the intensely hot and dense core of such an ultra-massive star as it approaches the very end of its short, brilliant life. In the star's central core region, where ambient temperatures routinely reach many hundreds of millions, or even billions, of degrees Kelvin, and where pressures and densities are almost beyond human comprehension, the star has, throughout its life, been systematically, layer by layer, fusing ever lighter chemical elements into ever heavier ones. Hydrogen becomes helium, helium becomes carbon, and so on, up the periodic table towards heavier elements. This continuous nuclear energy generation creates a powerful outward radiation pressure that normally balances gravity. But in stars exceeding roughly 130 solar masses, as core temperatures surpass several billion degrees, the incredibly energetic gamma-ray photons, which provide this crucial pressure, begin to behave strangely. Instead of just scattering, some transform via pair production into electron-positron pairs. These massive particles contribute little to outward pressure compared to the photons they replaced, as more photons convert to particle-antiparticle pairs. The core's radiation pressure dramatically, catastrophically drops. Gravity, ever waiting, then overwhelmingly takes over, the core, no longer supported, begins a rapid, unstoppable collapse. This is not a gentle fading, but a furious self-destruction driven by the star's own light. As the core contracts, pressures and temperatures build even more rapidly. Then, in a fraction of a second, the entire remaining fuel-rich core, primarily oxygen, neon, silicon, and magnesium, ignites almost simultaneously in a runaway thermonuclear conflagration. Unlike a normal core collapse supernova, this pair instability event explodes without significant prior core collapse to a neutron star or black hole. The sudden, complete fusion of the core floods it with an unimaginable amount of energy. Core temperatures spike to tens of billions of degrees. The entire star is literally, utterly torn apart from the inside out. No dense neutron star remnant is left. No black hole forms. Absolutely nothing of the original star remains, except a vast, rapidly expanding, incredibly hot cloud of newly synthesized gas and plasma, rushing outwards at thousands of kilometers per second. The star is not just disrupted, it is completely, irrevocably annihilated. This explosion comes not from running out of fuel, but paradoxically, from the star's own intense light becoming its agent of destruction. A runaway positive feedback loop culminating in total stellar self-destruction. The melancholy beauty of this event is its completeness. A star erased utterly from existence, its matter flung wide to enrich the cosmos. These titanic pair-instability supernovae are exceptionally rare today, predicted only for stars born within a narrow mass range, roughly between 130 and 250 solar masses. Smaller stars might experience some pair-instability but survive partially, perhaps shedding mass in violent pulsations before a more conventional collapse. Even larger stars might collapse directly into a black hole without such an explosive event. Unlike other supernova, pair-instability supernovae, by completely disrupting the star, release truly huge quantities of elements like oxygen, carbon, and silicon into interstellar space. These elements then become crucial building blocks for future generations of stars, planets, and potentially life. Astronomers suspect these explosions were more common in the early universe, when the first generation of stars, population 3 stars, are thought to have been much more massive and metal-poor. These colossal first stars likely ended their lives as pair-instability supernovae. Seeding the young cosmos with its first heavy elements, the James Webb Space Telescope is actively searching for the faint, ancient light from such primordial explosions. A few tentative candidates for more recent pair-instability supernovae have been observed, such as SN 2007 Bi, an unusually bright and long-lasting supernova whose properties match theoretical models almost perfectly. These events are crucial for understanding cosmic chemical evolution, explaining how certain elements appeared in large abundances so early in cosmic time. Each such explosion is a violent act of cosmic alchemy, transforming primordial simplicity into elemental complexity. Now, let us explore the dramatic ballet of stellar mergers, where binary stars, their orbits decaying over eons, spiral into a final, fiery coalescence. Many, perhaps most, stars exist not in isolation, but in gravitationally bound pairs, over vast timescales. These binary stars can lose orbital energy through gravitational wave emission or tidal interactions, causing them to spiral inwards. If this inward spiral continues, a catastrophic physical collision is inevitable. Stars are not solid objects, but spheres of hot plasma. When they finally touch, their outer gaseous layers intermingle and violently interact. Their dense cores are drawn closer, distorting each other until they merge into a single, larger, hotter, and often rapidly rotating, unstable object. The outcome depends on the masses, evolutionary stages, and compositions of the merging stars. If two main-sequence stars of similar mass merge, they can form a new, more massive main-sequence star, appearing brighter, hotter, and living a shorter life. Such objects might explain blue stragglers in old globular clusters, stars that appear anomalously young. Their youthful glow hides the violent merger that created them, a creative act born from destruction. However, not all stellar mergers are so neat. If one or both stars are more evolved, like a red giant, or if their masses are very unequal, the merger becomes incredibly messy and dynamically complex. A larger, diffuse star might engulf its smaller companion, leading to a common envelope phase where two cores orbit within a shared, turbulent gaseous envelope. Friction can heat this system intensely, often ejecting the common envelope, leaving behind a very close binary of the surviving cores. Or if the cores also merge, a single, highly evolved, rapidly rotating remnant. Sometimes, the energy released during such a merger creates a luminous red nova, a bright, reddish optical outburst less powerful than a supernova, but still visible across vast distances. One famous example was observed in 2008 in the Andromeda Galaxy. Another V1309 Scorpii in our galaxy was observed just as two contact binary stars merged, providing an unprecedented view of the entire process from inward spiral to final coalescence. Its brilliant glow was the direct thermal radiation from the moment of stellar contact, a testament to the universe's capacity for sudden, blazing transformations. When very massive stars merge, the outcomes are even more dramatic and energetically powerful. Vast quantities of stellar material are compressed, heated, and violently ejected. Their combined cores might ignite new, rapid phases of thermonuclear fusion. The turbulent mixing of elements can create spectacular light flashes and unusual chemical signatures. These newly formed, incredibly massive merged stars burn through their fuel at prodigious rates, dying young in spectacular supernova explosions far sooner than their progenitors would have. In some rare cases, the merger of massive stars or compact remnants like neutron stars or white dwarfs might even produce gamma-ray bursts, some of the most luminous explosions in the universe. Long gamma-ray bursts, in particular, might arise from the collapse of massive merged stars rotating so rapidly that they launch narrow beams of high-energy radiation. Even our own Milky Way galaxy is destined for a galactic-scale merger with Andromeda in billions of years. While individual stars are unlikely to collide directly due to vast interstellar distances, their orbits will be profoundly disrupted, potentially triggering stellar mergers within destabilized binary systems. The universe is a place of constant dynamic interaction where even the stately dance of stars can end in a violent, transformative embrace, scattering the seeds of future creation across the void. Each merger is a unique cosmic event, its fingerprint etched onto the surrounding environment, a story of union and upheaval written in light and gravity. Our journey now plunges into realms of unimaginable density, into the very heart of matter crushed beyond recognition. Beginning with neutron stars, these are the incredibly compact cores often left behind when a large star, typically between 8 and 25 times the Sun's mass, exhausts its fuel and dies in a supernova. A neutron star is astonishingly small, perhaps only 20 kilometers across the size of a large city, yet it packs more mass than our entire Sun. This extreme compression results in surface gravitational fields billions, even trillions, of times stronger than Earth's. Anything venturing onto its surface would be instantaneously and catastrophically crushed, its atoms torn apart by irresistible tidal forces and unimaginable pressure. The key to this is the extraordinary density of neutron star material. On Earth, we understand density in terms of how heavy something is for its size. But neutron star densities transcend terrestrial experience. Ordinary atoms cannot maintain their structure. Under the immense pressure, electrons are forced into protons, forming neutrons. These neutrons are packed shoulder to shoulder with almost no space between them, like a giant, city-sized atomic nucleus. A single teaspoonful of this matter would weigh around 10 million tons, more than all the buildings in a major city. The sheer weight of such density bends space-time itself, a silent testament to gravity's ultimate power. The outermost crust of a neutron star is thought to be a thin, incredibly rigid layer of atomic nuclei and degenerate electrons, with atoms stretched into long, needle-like chains by the intense gravity and magnetic fields. Deeper inside, conditions become even more exotic and less understood. Nuclei dissolve, and neutrons may behave as a quantum superfluid, flowing almost without friction. Deep within the core, pressure warps space-time significantly. Time ticks more slowly near a neutron star's surface compared to a distant observer, a phenomenon of gravitational time dilation. Light paths are visibly bent, allowing an observer to potentially see more than half the star's surface at once. Born from the collapse of rapidly spinning stellar cores, neutron stars typically rotate very quickly due to conservation of angular momentum. Many spin several times a second. Millisecond pulsars, often spun up by accreting matter from a binary companion, can complete hundreds or nearly 1,000 rotations per second. These rapidly spinning, highly magnetized neutron stars are observed as pulsars, emitting beams of radiation from their magnetic poles. Each sweep of a beam across our line of sight registers as a precise pulse. So regular, they rival atomic clocks and are used in projects to detect long-wavelength gravitational waves. The gravity's effect on infalling matter is profound. A pebble hitting a neutron star's surface would do so at about half the speed of light, releasing an enormous burst of energy. This is why X-ray binaries, where a neutron star accretes matter from a companion, are so intensely bright in X-rays, as infalling material crashes onto the neutron star, heating its surface to millions of degrees. The exact state of matter at the very center of a neutron star, where pressures are even more extreme, remains a subject of intense theoretical debate. Some models suggest neutrons might deconfine into their constituent quarks, forming quark matter or a quark-gluon plasma. Others propose the existence of exotic hadronic particles like hyperons. These conditions are impossible to replicate on Earth, making direct experimental verification elusive. What prevents a neutron star from collapsing further into a black hole is neutron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, which forbids identical fermions like neutrons from occupying the same quantum state. This pressure supports the star against gravity up to a critical mass limit, the Tolman-Oppenheimer-Volkoff limit, estimated to be around 2 to 3 solar masses. If a neutron star accretes too much mass and exceeds this limit, even neutron degeneracy pressure fails, and it collapses catastrophically into a stellar mass black hole. Neutron stars also possess incredibly strong magnetic fields, sometimes trillions or quadrillions of times stronger than Earth's. These ultramagnetic neutron stars, known as magnetars, can experience violent starquakes in their crusts, releasing huge flares of gamma rays and X-rays. A powerful magnetar flare from a nearby source could potentially damage Earth's atmosphere and biosphere. Though thankfully, all known magnetars are safely distant. These crushed cores, spinning with furious speed and wrapped in unimaginable magnetic fields, are laboratories for extreme physics, their existence pushing the boundaries of our understanding of matter and gravity. Now, let us consider an even more speculative, yet theoretically plausible, and potentially even more energetic cosmic event, the Quark-Nova conjecture, which proposes the possibility of a hypothetical, powerful second blast occurring shortly after a star has already died in a supernova. For decades, it was thought that matter couldn't be packed more tightly than in a neutron star, unless it collapsed into a black hole. The Quark-Nova idea challenges this what if. Under even more extreme conditions, the story doesn't end with stable neutron matter. If the internal pressure within an existing neutron star continues to rise, perhaps due to rapid accretion or a subtle shift in core conditions, it might cross a new critical stability limit. At this point, the Quark-Nova theory suggests individual neutrons could deconfine, dissolving into their constituent quarks, forming an even denser state of matter known as quark matter or a quark-gluon plasma. This phase transition from neutron matter to quark matter would likely cause a sudden, violent, additional gravitational collapse of the neutron star's core, followed by an equally violent, explosive bounce back. The energetic result would be a powerful, distinct second stellar explosion, a quark nova. This secondary blast, following the primary supernova by perhaps hours or days, would send out another burst of energy, particles, and possibly newly synthesized elements, significantly reshaping the supernova remnant. If quark novae are real and occur with significant frequency, they could explain anomalous features in some supernova light curves and spectra, such as unexpected rebrightenings or unusual emission lines that standard models struggle to account for. These secondary explosions might offer a window into physics beyond the neutron star state, a realm of even more extreme matter. Some theoretical models of quark novae suggest this secondary explosion could launch its own relativistic jets or release distinct bursts of gamma rays, potentially contributing to the brightest superluminous supernovae. Furthermore, while normal supernovae forge many heavy elements, the incredibly neutron-rich environment of a newly formed neutron star is ideal for the R process, creating elements far beyond iron. If a subsequent quark nova disrupts this neutron-rich core, it could scatter these very heavy, rare elements into space, their unique chemical fingerprints potentially appearing in ancient beige, metal-poor stars or future planetary systems. An even more speculative outcome is the formation of stable, strange quark matter. Some theories propose that once deconfined quark matter forms, it could be even more stable than ordinary nuclear matter. If a seed of this ultra-stable strange quark matter appears, it might trigger a runaway conversion of the entire neutron star into a quark star, an even more exotic and compact remnant. These purely hypothetical quark stars remain unobserved, but represent a possible end state for matter under extreme pressure. A quark nova could be the transformative process creating them, tiny fragments of this strange quark matter. Strangelets might even be ejected, flying invisibly through the galaxy. Verifying these theories is challenging, as we cannot replicate such extreme conditions on Earth. However, the quark nova idea offers an intriguing lens to understand the complex final moments of some massive stars, suggesting that even after a star has died once, something deeper, more fundamental, can break free, unleashing enough power to rip its core apart one final spectacular time. The universe, it seems, may hold layers of explosive potential within its densest objects, a series of apocalypses nested within each other. The journey into extreme cosmic events now brings us to Kilanova explosions, born from the cataclysmic mergers of neutron stars, serving as cosmic forges for the rarest elements in the quiet corners of the universe. Two neutron stars, remnants of massive stars, can orbit each other in a slow death dance lasting millions or billions of years. Due to the emission of gravitational waves, ripples in space-time predicted by Einstein, their orbital energy slowly drains, causing them to spiral inexorably closer. Their orbital speeds increase dramatically, approaching a significant fraction of the speed of light in their final moments. Eventually, they catastrophically collide, unleashing one of the most powerful and scientifically informative explosions, a kilonova. These events are rare, perhaps occurring only once every few tens or hundreds of thousands of years in a galaxy like the Milky Way. As the neutron stars merge, the system emits increasingly strong gravitational waves. When they finally crash, they tear each other apart. Huge amounts of incredibly dense, neutron-rich matter, perhaps many moon masses or even a few percent of a solar mass, are violently flung into space at extreme speeds, often approaching 1/3 to 1/2 the speed of light. This ejecta is uniquely neutron-rich, creating perfect conditions for the R process. In the rapidly expanding, cooling ejecta, free neutrons are rapidly captured by lighter atomic nuclei, building up progressively heavier, unstable isotopes. These then undergo radioactive beta decays, transmuting into more stable, heavier elements. In mere seconds, complex chains of very heavy elements, like gold, platinum, silver, and uranium, are formed. These elements are not significantly produced in ordinary stars or most supernovae. Kilonovae are believed to be their primary cosmic source. Without these rare events, such precious elements would be virtually non-existent. The light from a kilonova is distinctive. Its brightness rises very quickly, within a day or two of the merger, reaching a peak luminosity often comparable to or slightly less than a typical supernova. It then fades rapidly over a week or two. Its color evolves dramatically, typically from an initial hot, bright blue to a cooler, fainter, redder, or near-infrared hue as heavy R-process elements form and increase the ejecta's opacity. In 2017, astronomers witnessed GW 170817, the first confirmed Kilanova. Detected through both gravitational waves and subsequent electromagnetic radiation across the spectrum. Two neutron stars merged about 130 million light-years away. The gravitational waves arrived first, followed seconds later by a gamma-ray burst, and then by optical and radio afterglow. This event is estimated to have produced dozens of Earth masses worth of heavy R-process elements, including enough gold to fill Earth's oceans many times over. A few such events over billions of years can significantly enrich vast regions of interstellar space. What remains after the merger depends on the total mass. If it exceeds the Tolman-Oppenheimer-Volkoff limit, the remnant likely collapses rapidly into a black hole. If slightly less, a hypermassive, rapidly spinning neutron star might form temporarily before collapsing. During this brief phase, strong, wound-up magnetic fields and rapid rotation can launch powerful relativistic jets, believed to produce short-duration gamma-ray bursts, lasting less than 2 seconds. Gravitational wave detectors like LIGO and Virgo allow scientists to pinpoint these mergers and alert other telescopes, enabling multi-messenger astronomy. By studying the light and spectra of kilonovae, we learn how heavy elements form, how the explosion evolves, and what kind of remnant is left. Much of the gold, platinum, and uranium in our solar system likely originated from ancient kilonovae, their elemental bounty incorporated into the clouds that formed our Sun and Earth. We literally carry the results of these distant, violent stellar collisions, a tangible link to the universe's most creative and destructive moments, a melancholy beauty in the ashes of dead stars reborn as precious matter. Our exploration now confronts the universe's most extreme engines, beginning with magnetars, neutron stars wielding magnetic fields of such incomprehensible strength they can trigger starquakes and colossal gamma-ray flares. These are true magnetic leviathans. A typical magnetar's magnetic field can be 1,000 times stronger than a normal neutron star's, reaching up to a quadrillion times stronger than Earth's geomagnetic field. These fields are so potent they don't just influence nearby space, they actively reshape matter itself, distorting atoms, altering chemical bonds, and even affecting the quantum vacuum. Light behaves strangely near such fields, becoming polarized or scattered in unusual ways. Even empty space near a magnetar's surface can act like a prism, bending light. Most of the time, magnetars are relatively quiet, rotating slowly and emitting low levels of X-rays or gamma rays. But then, without warning, they can erupt in giant flares. In less than a second, a magnetar might release more energy than our Sun does in 100,000 years. These flares are not from nuclear fusion or gravitational collapse, but from the magnetic field itself. Over time, the field twists and strains the magnetar's solid crust. Like Earth's crust cracking in an earthquake, the magnetar's crust can snap. The stored magnetic energy is released all at once as a massive outburst of gamma rays and X-rays. One famous flare on December 27, 2004, from SGR 1806-20. Temporarily altered Earth's ionosphere and overwhelmed satellite detectors. If it had been much closer, it could have caused significant atmospheric damage. These events are rare, but highlight the immense, dormant power locked within these objects. These giant flares are rare, but smaller bursts might happen more regularly, especially in young magnetars. Even these can rival the Sun's energy output. Magnetars exist at the edge of known physics, their fields challenging quantum theory and general relativity. No terrestrial laboratory can replicate these conditions. They are natural crucibles for extreme physics. There's also a potential link between magnetars and fast radio bursts, powerful millisecond duration radio pulses of unknown origin. In 2020, a magnetar in our galaxy emitted a radio burst simultaneously with X-rays, suggesting a connection, though the burst was weaker than FRBs from distant galaxies. Magnetars are thought to have short active lives. Their magnetic fields decay over thousands of years, and they eventually become quiet neutron stars. This makes them hard to find, with only a couple of dozen candidates known. Satellites like Swift and Fermi constantly scan for high-energy flashes, hoping to catch these fleeting eruptions. The exact formation mechanism of magnetars remains debated. Perhaps they are born from very massive, fast-spinning stars, or perhaps from post-supernova interactions. Regardless, once formed, a magnetar is a ticking time bomb, its serene surface belying the magnetic fury within, a beautiful yet terrifying concentration of electromagnetic power. Fast radio bursts, first detected in 2007, remain one of modern astronomy's great mysteries. These are millisecond-long flashes of incredible radio power, appearing suddenly and then vanishing. Unlike predictable signals from pulsars or quasars, FRBs are enigmatic. They release as much energy in a millisecond as the Sun does in a day. Yet their sources are often invisible in other wavelengths. Initially suspected as glitches, their consistent detection from deep space confirmed their astrophysical reality. Theories abound. Some suggest they are related to explosive events in massive stars or the collapse of dense objects like magnetars. The connection to magnetar flares is compelling. Others propose cataclysmic events involving black holes, like collisions or a black hole consuming a neutron star, though direct evidence is lacking. More exotic theories, including signals from advanced extraterrestrial technology, are considered, though without concrete support. Most FRBs are single flashes, but some repeat at random intervals, suggesting a non-catastrophic, repeatable source. These repeaters offer better opportunities for study. All detected FRBs originate outside the Milky Way, often billions of light-years away, their immense power challenging our understanding of energy generation. As radio waves from FRBs travel through intergalactic space, they interact with electrons, causing delays and scattering. Studying these effects provides insights into the diffuse matter between galaxies. Repeating signals hint at active magnetars or neutron stars in binary systems, where intense magnetic fields create periodic bursts. Observatories worldwide continue the hunt, seeking to unravel the origin of these powerful, fleeting cosmic whispers, signals that briefly illuminate the vast, dark voids. Their ephemeral nature holds a certain melancholy beauty, like messages in bottles cast into the cosmic ocean. Finally, we confront the ultimate engines of cosmic power black holes and the dramatic phenomena associated with their insatiable hunger. Black hole formation itself is a testament to gravity's relentless might. When a truly massive star exhausts its nuclear fuel, its core collapses under its own weight. If the star is sufficiently massive, even neutron degeneracy pressure cannot halt the collapse. The core implodes, shrinking towards infinite density, forming a singularity. Around this, an event horizon materializes, the point of no return, beyond which nothing, not even light, can escape. While the black hole is hidden, its birth is often announced by a supernova explosion, releasing vast energy as neutrinos, electromagnetic radiation, and shock waves that disperse heavy elements and can trigger new star formation. Many stellar mass black holes exist in binary systems, accreting matter from a companion star. This infalling material forms a hot accretion disk, emitting intense X-rays that allow us to detect and study the black hole's properties. Sometimes, these black holes merge with other compact objects, emitting detectable gravitational waves, the very existence of black holes, with their singularities and event horizons where known physics breaks down, challenges our fundamental understanding of the universe, a profound mystery at the nexus of gravity and quantum mechanics. Black hole hyperaccretion represents an even more extreme phase, where black holes feed at rates far beyond their usual capacity. The accretion disk becomes supercharged, with matter spiraling inward at near-relativistic speeds. This frenzy generates massive, collimated jets of plasma and radiation, blasting outwards for millions of light years, making these objects some of the most powerful and luminous in the universe. This typically occurs when a large influx of matter from galactic mergers, gas clouds, or tidally disrupted stars becomes available. The accretion disk heats to millions or billions of degrees, emitting vast radiation across the spectrum, often outshining its entire host galaxy by factors of thousands or millions. This powerful radiation can even push away infalling material, creating a self-regulating feedback loop. The jets launched during hyperaccretion are thought to be driven by powerful magnetic fields generated by the spinning black hole and the turbulent accretion disk. Material from the innermost disk is accelerated and funneled outwards along the black hole's rotational axis. These jets are visible across cosmic distances, especially from active galactic nuclei in young, distant galaxies. The energy carried by these jets can profoundly influence the host galaxy, heating interstellar gas and suppressing star formation, a process known as AGN feedback, crucial for regulating galaxy growth. Quasars are iconic examples of hyperaccreting supermassive black holes, initially appearing star-like. Their large redshifts reveal them as incredibly distant and luminous galactic centers, their light often taking billions of years to reach us. They offer a window into the early universe, allowing study of early black hole and galaxy evolution. The intense radiation from quasars also played a key role in cosmic reionization, transforming the early universe from a neutral, opaque fog to the transparent, ionized state we see today. Blazars are an even more extreme class of AGN, where the relativistic jet happens to be pointed almost directly at Earth. This alignment causes relativistic boosting, dramatically amplifying the jet's apparent brightness and energy due to the principles of special relativity. Blazars are among the most energetic, luminous, and rapidly variable objects known. Their jets can outshine the entire accretion disk and host galaxy, their brightness fluctuating on timescales of hours or days due to turbulent processes within the jet. This rapid variability allows us to probe the innermost regions near the black hole and the jet launching mechanism. Blazars emit radiation across the entire electromagnetic spectrum, from radio waves produced by synchrotron radiation to high-energy X-rays and gamma rays from inverse Compton scattering. Their distant light, traveling for billions of years, can be used as a probe of the intervening intergalactic medium and the large-scale structure of the universe, even offering indirect ways to investigate dark matter and dark energy. A famous example is 3C279, a benchmark object for studying relativistic jets. The Fermi Gamma Ray Space Telescope has been instrumental in discovering and studying many blazars at high energies. These cosmic lighthouses, powered by the universe's ultimate engines, illuminate the deepest, darkest, and oldest corners of existence. A more transient, yet equally spectacular display of black hole power is the tidal disruption event, when an ordinary star wanders too close to a galaxy's central supermassive black hole. The black hole's immense tidal forces, the difference in gravitational pull across the star, can overwhelm the star's own gravity. the star is stretched into a cosmic spaghetti strand and violently torn apart. This disintegration releases a brilliant, short-lived burst of radiation, primarily in ultraviolet and soft X-rays, as stellar material is shredded, accelerated, and compressed. Unlike persistent AGN accretion, TDEs are fleeting, one-off events. Much of the disrupted debris is scattered into eccentric orbits, with only a fraction falling back to form a temporary luminous accretion disk, causing a dramatic spike in the black hole's luminosity. The energy released can briefly outshine the entire host galaxy by hundreds of times, making TDEs visible across vast cosmic distances. Such events occur when a star's orbit is perturbed, perhaps by interactions within the dense central star cluster. Once a star crosses its tidal radius, its demise is inevitable. The ejected stellar material, enriched with elements forged in the star's core, is spread through the host galaxy, influencing its chemical evolution. Observing the TDE flare's light curve, color, and spectra provides unique clues about the black hole's mass and spin, and the physics of extreme accretion. However, these events are short-lived, often fading within months, making them challenging to detect and study in their crucial early stages. Each TDE is a brief, violent illumination of a black hole's destructive power, a star's final scream echoing across the cosmos, a melancholy testament to the indifferent gravitational titans that lurk at the hearts of galaxies. Our voyage through the realms of cosmic power, from the whisper of a lone particle to the roar of colliding galaxies, draws to a close. We have witnessed the universe in its most extreme states, where energy and matter are forged and annihilated in crucibles of unimaginable scale. We have seen stars born from violence and dying in spectacular, element-scattering explosions, worlds adrift and worlds consumed, and the silent, inexorable dominion of gravity, culminating in the enigmatic darkness of black holes. What is the most powerful thing in the universe? Perhaps it is not a single entity, but the relentless, transformative process itself. The constant interplay of creation and destruction, the delicate balance forever teetering on the edge of cosmic apocalypse. The melancholy beauty we find in these events is not in the destruction itself, but in the profound, indifferent grandeur of the cosmos. A universe that operates on scales and with forces so far beyond our terrestrial experience that they inspire both awe and a deep humility. These cosmic titans, from supernovae to quasars, are not merely destructive. They are integral to the universe's ongoing evolution, scattering the very elements that make up stars, planets, and ultimately ourselves. We are, in a very real sense, forged from the ashes of these cosmic fires, our existence a fleeting, intricate dance on a small stage in a vast, dynamic, and often violent cosmic theater. As we continue to peer deeper into the void, armed with ever more sophisticated instruments and an insatiable curiosity, we uncover more of these powerful secrets. Each discovery reminds us of how much we still have to learn, how many more layers of reality await our understanding. The universe does not yield its truths easily, but in every answered question, new, more profound mysteries emerge. The quest to comprehend these ultimate powers is a journey into the heart of what it means to be a conscious observer in such a universe. A tiny spark of awareness capable of contemplating the infinite, and in that contemplation, perhaps, lies a power of its own, the power to wonder, to explore, and to find a strange, poignant beauty in the ephemeral light against an eternal, powerful darkness. The echoes of cosmic fury will continue to resonate, shaping the universe long after our brief moment has passed, a timeless symphony of power and transformation.